Unit 1, Section 1, Earth's Atmosphere. The atmosphere of the Earth is a thin layer of gases surrounding the Earth and is broken up into layers. Now, if you were to look at the Earth from outside, from space, you would see the atmosphere, but it really looks really thin. It's almost like the skin of an apple. That's about how thin it is compared to the size of the Earth. Now, the atmosphere is made up of mostly nitrogen, 78% nitrogen gas, 21% oxygen, 0.9% argon. Now, if you add those three up, that's 99.9% of our atmosphere is made up of three gases. Now, nitrogen is actually two nitrogen atoms combined together. That's the nitrogen that makes up our atmosphere. The oxygen is two oxygen atoms combined together, forming an oxygen molecule. And argon is by itself. Now, the remaining is made up of various gases, including water vapor and carbon dioxide. But water vapor changes way too much. So it changes so much that we can't really put down a percent for the water vapor. You can talk about our humidity, which is kind of a measure of how much water is in the air. That changes so much from day to day that there's no percent. Whereas nitrogen, oxygen, argon, those are pretty much the same percents almost all the time. Now this is a little graphic showing the different percentages of each of the gases. Again, nitrogen 78%, oxygen 21%, argon 0.9%. Next on the list is carbon dioxide, but that's only 0.035%. It's a very small amount of the atmosphere. And the rest of the gases combined are only 0.065%. So you can see this nice little pie chart here. You can see how much nitrogen is. And then oxygen is the next big chunk, and then all the rest kind of make up a tiny bit. Now, the thing is that even though they make up that tiny bit, that's still very important to us because we have gases like carbon dioxide here, carbon dioxide, which is a greenhouse gas, which is very useful in regulating the Earth's temperature. Or we have gases like ozone here. Ozone blocks ultraviolet light in the top of the stratosphere, and that's very useful because without that, trust me, you get really, really bad skin burns. Helium is a very light gas. We get very little of that. Hydrogen, I mean, this is such a tiny amount in our atmosphere as hydrogen. Most of that escapes the atmosphere. So you can see most of the other gases that make up our atmosphere. Now there are two very important processes that occur in the atmosphere that deal with oxygen and carbon dioxide. First one is photosynthesis, where plants use carbon dioxide, so they take that in, and water and energy, and they convert into food energy. So we have carbon dioxide, that's that right there. We have water, that's the symbol for water. And we take in sunlight from the sun, and it produces sugar, which is stored plant energy, and then oxygen here. This is the gas that we breathe in. That's very important for us to live. So plants take in carbon dioxide, water, and energy, produce sugar and oxygen. Now the opposite of photosynthesis is respiration. Now technically plants do also carry out respiration, but they carry out photosynthesis so much more than respiration that the net gain is photosynthesis. Respiration, animals use oxygen to convert sugar into food energy that they can use. It's pretty much the opposite of photosynthesis because we start with the sugar, add oxygen, our bodies break that down, and we spit out carbon dioxide, we get water, and then we get usable energy from that. Think about all the stored energy in your body, all the sugars that you have. Now I'm just talking about pure sugar. Sugar is talking about eating glucose or sucrose. With this, then we're taking those sugars combined with oxygen, producing carbon dioxide, water, and energy. So photosynthesis produces oxygen, respiration produces carbon dioxide by using that oxygen. Now, another thing that goes on in the atmosphere is the water cycle. Water is in constant motion in our atmosphere. It moves from the surface to the air, back to the surface. It can go underground. It can end up atop of a mountain. And so you see this water cycle. Now, I know it kind of looks like a circle, but you really can't think of it like a circle because, well, let's look at the water that's in Low Wall Lake. That got there mostly from rain. And so water went to the atmosphere to make that rain. Well, that water came from probably somewhere west of here. So it could be even somewhere from the Pacific Ocean. That water went up into the air and eventually fell down here as rain, got into Low Wall Lake. Well, there it can get soaked up by the soil. It can evaporate back into the atmosphere, or it can move around a lot of different ways. Now, a lot of these terms are going to be pretty simple. Evapotranspiration, that's a new one. That is when water is released by plants. So water leaving a plant, we call that evapotranspiration. Condensation up here, that's when it goes from a gas to a liquid. It condenses. Think about like if you had a glass of ice water and you get the water that forms on the outside of the glass. Well, that's condensation. That's when water vapor out of the air goes from gas to liquid on top of the glass. Precipitation, of course, is water falling down, whether that's rain, snow, sleet, whatever. Then we have a lot of groundwater. Of course, is water that's found underground. Water can be stored in ice and snow. It can be stored in glaciers. There's water stored in continental glaciers that's been there for thousands upon thousands of years. We can actually measure the age of it. Now, another aspect of the atmosphere is air pressure. Air pressure is the force of the air weighing down over a unit of area. Now, it doesn't feel that way to you, but you're holding up all the air above you, in a sense. And that's all pushing down on you. But we are not crushed because the molecules in our bodies are pushing outward to compensate. So we do not get crushed by the air, even though the air is very, very heavy because of the pressure inside of our own bodies. At sea level, standard atmospheric air pressure is around 14.7 pounds per square inch. That means that if I were to draw out 1 square inch, an inch by inch square, there'd be 14.7 pounds pushing in on that. Now think about that for a second, and think about the size of your body, how many square inches your body would be, and how many total pounds pushing in on you. So the air is very, very heavy. Now, this is easier for us to understand. Maybe think about water pressure. You go deep under the water, and the water's pushing on you, squeezing you down. Subs can be crushed by it. We think about that more so than the air pushing on us, but it's the same thing. It's pushing in. As you go up in the atmosphere, because there's less air, the air pressure decreases. So, as you go up in the atmosphere, you go higher and higher, the air pressure decreases. For about each 6 kilometers, the air pressure decreases about half. Most of the air in the atmosphere is found in the bottom. When we have almost all of the air by mass is found at the bottom. It settles down there, the lighter stuff as you go up. Now, density is a term you should definitely remember from 8th grade physical science. Density is equal to the number of molecules given volume. We remember it as finding it by mass divided by volume gives us density, and that's a symbol for density there. As you go higher into the atmosphere, density decreases. So the density of the air decreases as you go up. The molecules are farther apart the higher you go in the atmosphere. In higher altitudes, you have to breathe in more to get the same amount of oxygen as you would at lower altitudes. So low altitudes, we have all these molecules which are tightly packed together. There's almost no space between them. There is, but it's very, very small, hard to measure. But as we go up in the upper levels of the atmosphere, they get farther apart. And so think about your lungs for a second. You can only take in so much. You have to pull in a lot of material to get the same amount of oxygen. So higher altitudes, there's more separation, so there's less mass and the same amount of volume.